problem, traffic, optimizing traffic flow through a network of roads.
More like city planning or something.
Yep, you're finding the maximum flow of traffic from a source to a sink using algorithms like Ford-Fulkerson or Edmonds-Karp.
Real-world applications for sure.
Absolutely. Chapter 10 really showcases those advanced graph algorithms and how they can be applied to finance, time travel, traffic, all sorts of things.
Graphs are way more powerful than I thought. What's next?
Chapter 11 introduces dynamic programming, a technique that can make algorithms way faster for certain types of problems.
Dynamic programming. Okay, break that down for me. What's the idea?
It's about breaking a problem into smaller, overlapping subproblems. The key is you store the solutions to those subproblems so you don't have to recalculate them every time.
Like remembering the answers to things you've already figured out.
Exactly. Save yourself the work. Be efficient. Chapter 11 explains the principles, like optimal substructure and overlapping subproblems.
Okay, optimal substructure and overlapping subproblems. Remind me what those are.
Sure. Optimal substructure means that the best solution to the whole problem relies on the best solutions to its parts. Like if the shortest path from A to C goes through B, then the shortest paths from A to B and B to C got to be optimal too.
Makes sense. The overall solution depends on those smaller solutions being the best they can be.
Right. And overlapping subproblems means you're solving the same smaller problems multiple times. Like when you calculate the Fibonacci sequence, you keep calculating the same Fibonacci numbers over and over.
So instead of repeating that work, you store the answers and just look them up.
Exactly. That's dynamic programming in a nutshell. The chapter uses a classic example, the edit distance problem.
Edit distance, I'm not familiar with that one.
It's about finding the fewest changes to turn one string into another, inserting characters, deleting them, substituting them.
So like how many edits to change cat to dog?
Exactly. Dynamic programming solves this by breaking it down, comparing prefixes of the strings. You build a table of edit distances between all those prefixes, and that lets you calculate the distance for the whole strings efficiently.
Building up the solution from those smaller pieces.
You got it. And the chapter shows how to do that, how to find the best solution, and also how to reconstruct the steps you took to get there, which is pretty neat.
So like leaving a trail of breadcrumbs to retrace your steps.
Perfect analogy. Chapter 11 gives you the foundation for dynamic programming, lots of potential for solving tough problems efficiently.
Definitely seems powerful. What kind of problems does Chapter 11 have?
Well, there's cutting sticks, where you're cutting a stick into pieces, trying to minimize the cost of cutting. Got to figure out the best order to make those cuts.
Like optimizing a woodworking project or something?
Yep. Dynamic programming helps break that down, find the best way to cut each smaller segment, then combine those solutions for the whole shtick.
Divide and conquer, but with this extra layer of storing solutions.
Right. Then there's the marriage problem, classic matching problem. Men and women, each with preferences, gotta pair them up in a stable way where no two people would rather be with someone else.
Matchmaking with an algorithm.
Exactly. It's used in lots of areas, matching students to hospitals or even just roommates. Dynamic programming, along with algorithms like the Gale-Shapley algorithm, can solve this efficiently.
Algorithms for love, that's wild.
It is. Shows how broadly applicable these ideas are. Then there's the distinct subsequences problem, counting how many different subsequences are in a string.
Subsequences, so like all the different words you can make from a bigger word, even if the letters aren't next to each other.
Exactly. Dynamic programming helps break that down, count subsequences of smaller parts of the string, build up to the whole thing.
Pattern seems to be break it down, solve the small parts, combine them.
You're getting it.
Ah.
Chapter 11 shows how dynamic programming can be used for all sorts of things, optimizing, matching, even counting.
I'm starting to see the potential here. So what's next?
Chapter 12 takes us into the world of grids. We're moving away from those abstract concepts and into something more concrete.
Grids, like you'd see in a game or a spreadsheet.
Exactly. Chapter 12 is all about working with those two-dimensional arrays that represent grids. They're great for modeling spatial data, images, game boards.
More visual, more tangible.
For sure. The chapter covers representing grids, different types, common operations, and then algorithms for solving grid-based problems.
So the basics of grids, and then how to use them to solve problems.
So that's the idea. It starts with representing grids using two-dimensional arrays. Each cell in the array is a cell in the grid.
A digital representation of a physical grid.
Exactly. And then it gets into different types of grids. Rectangular, triangular, hexagonal.
Different shapes. Why would you need different shapes?
It depends what you're modeling. Hexagonal grids are popular for games and simulations. They represent space more naturally than just squares.
Like choosing the right Lego brick for the job.
Exactly. Chapter 12 talks about those different grid types, their properties, how to work with them. Then it covers common operations, accessing cells, changing them, iterating over elements, doing calculations on neighboring cells.
So the basic moves for working with a grid.
Yep. And it talks about efficiency too, especially for large grids or sparse grids where most cells are empty.
Sparse grids, so like
Yeah,
a map where most of it is ocean. So you don't need to store every single ocean cell.
exactly. You can use special data structures to store only the important stuff, save space and time. Then the chapter gets into coordinate systems.
Coordinate systems like latitude and longitude.
That's a good example. Chapter 12 explains different coordinate systems, how to specify locations in a grid, how to convert between systems.
So like using different maps to navigate the same area.
Exactly. And it talks about real-world applications of grids for mapping, geographical data, using latitude and longitude, calculating distances on a sphere.
So grids for modeling the Earth. Pretty cool.
It is. Now, the problems in this chapter are pretty fun. There's ant on a chessboard, where you're tracking an ant's movements based on certain rules.
So simulating the ant moving on a grid.
Exactly.
Yeah.
You got to figure out where it ends up after a certain number of moves, using coordinates, patterns, maybe even modular arithmetic to be efficient.
Mixing grids and math. Neat.
Then there's the monocycle, a unicycle navigating a grid-based city, changing direction based on color changes on the grid.
So programming a unicycle sounds challenging.
It is. You got to track the unicycle's position and its direction. Good for understanding coordinates, directions, those changes in state.
Like a little robot navigation problem?
Kinda. Then there's the bee maja problem, finding the shortest path for a bee to visit all the flowers in a honeycomb, which is a hexagonal grid.
Bees, honeycombs, and algorithms. Who knew?
It's a classic. You're using hexagonal grids, shortest path algorithms, maybe even dynamic programming to optimize that bee's route.
Chapter 12 really shows how grids can model so many things.
They're super versatile, for sure. Now, Chapter 13 takes us into geometry, algorithms for points, lines, shapes.
Geometry takes me back to high school. Triangles, circles, proofs.
We'll skip the proofs this time. This is about solving those geometric problems with code. It's computational geometry, a whole field that combines geometry and computer science.
So using algorithms to figure stuff out about shapes and where they are in space.
Exactly. Chapter 13 starts with a refresher on those high school concepts, Pythagorean theorem, trigonometry.
Brushing up on the basics.
Got to have that foundation. And the chapter shows how to use those concepts to calculate distances, areas, angles.
Practical stuff, like how far apart are 2 points, or what's the area of this triangle.
Exactly. Then it gets into representing those geometric things in a computer. Points as coordinates, lines as equations, shapes as combinations of points and lines.
Teaching the computer how to understand geometry.
That's the key. Once you've got that, you can use algorithms to solve all sorts of problems, like, do these two line segments intersect? What's the area of this polygon? How far is this point from this line?
Automating those geometry calculations.
Precisely. This stuff is used all over. Computer graphics, robotics, those geographic information systems. And Chapter 13 also talks about handling special cases, like what happens when lines are parallel or points all lie on the same line.
So those edge cases that could mess up your calculation.
Exactly. Got to make those algorithms robust. Now, for the problems, there's dog and gopher. Classic chase scenario. Dog's trying to catch a gopher. Gopher's trying to reach a hole for safety.
Sounds like a cartoon.
It's a fun one. You got to figure out if the gopher can make it before the dog catches it. It's about distances, speeds, that geometry of the situation.
Geometry in action.
Exactly. Then there's chocolate chip cookies, a circular cookie with chocolate chips randomly scattered in it.
Okay, now you're speaking my language.
You break the cookie along a random line. Got to figure out the probability of getting at least one chip on both halves.
So geometry meets probability and cookies.
A delicious combination. Then there's is this integration. You've got a bunch of line segments, got to figure out if there's a horizontal line that intersects all of them.
Like finding a line that cuts through everything.
Precisely. Good for understanding lines, potentially using sorting and searching to solve it efficiently. Chapter 13 shows the range of those computational geometry problems, the different techniques involved.
Definitely seeing the applications here. So what's left? We got one more chapter, right?
Yep, just one more. Chapter 14, and this one's all about those more advanced computational geometry algorithms, building on what we saw in Chapter 13.
Taking it to the next level.
Exactly.
Yeah.
This chapter gets into things like convex hulls, line segment intersection, polygon triangulation, point location.
Some of that stuff sounds pretty complex.
It can be, but the chapter explains it well. It starts with convex hulls. That's the smallest convex polygon that encloses a set of points.
Convex polygon. Got to refresh my memory on that one.
Sure, it's a polygon where all the interior angles are less than 180 degrees. Or, another way to think about it, if you connect any 2 points inside the polygon with a straight line, that whole line stays inside.
So no dents or inward curves.
Right. Think of it like stretching a rubber band around all those points. The shape the rubber band makes, that's the convex hull.
Ah, that makes sense.
Yeah.
So how do you actually find that convex hull with code?
Chapter 14 presents two classic algorithms, Gram-Scan and Jarvis-March.
Two different ways to do the same thing, huh?
Yep. Both work, but they approach it differently. Gram-Scan sorts the points, then builds the hull 1 point at a time, getting rid of points that wouldn't make it convex. Jarvis-March starts with a point on the hull and keeps finding the next point by looking for the one that makes the smallest angle.
So Gram-Scan's like building a fence outwards, and Jarvis March is like walking along the edge, always turning left.
Perfect analogies. They both have their uses. Then the chapter moves on to line segment intersection, figuring out if two line segments cross.
Pretty straightforward, right? Just see if the lines overlap.
It can get tricky when you have lots of lines, and efficiency matters. This stuff is used in collision detection, path planning, all sorts of things. Chapter 14 talks about algorithms like the Bentley-Ottman algorithm and the sweep line algorithm for finding those intersections.
So handling lots of lines, finding all the crossing points.
Exactly. Important for analyzing geometric data, finding conflicts. Then it's on to polygon triangulation, breaking a polygon up into triangles.
Why would you want to do that?
Triangles are simpler, easier to work with for a lot of calculations and algorithms. Chapter 14 shows an algorithm called ear clipping to do this efficiently.
Ear clipping. What's that?
It finds these ears in the polygon, triangles that stick out, and removes them one by one until you're just left with triangles.
Like carefully taking apart a puzzle.
Kind of. And lastly, the chapter covers point location, figuring out if a point is inside or outside a polygon.
Like, is this point within this region on a map?
That's it. Useful for mapping, graphics, all sorts of things. The chapter talks about the ray casting algorithm. You imagine shooting a ray from the point, see how many times it crosses the polygon's edges, odd number of crossings, it's inside, even it's outside.
Oh, that's clever, like shining a light and seeing how many walls it hits.
Exactly. Now, the problems in this chapter are pretty challenging. There's the closest pair problem, finding the two closest points in a set.
Like finding the two stars closest to each other.
Exactly. Lots of applications, from pattern recognition to collision detection. Efficient algorithms for this, like using a divide and conquer approach, are really important, especially for large data sets.
Divide and conquer. Break it down. Solve the small parts. Combine the solutions. That sounds familiar.
It's a powerful pattern. Then there's polygon area, calculating the area of a polygon, given its vertices.
So just like finding the area of any shape, but doing it with code.
That's it. And then there's that point and polygon problem again, but now it's tougher, more complex shapes, potentially lots of points to check.
Really putting those algorithms to the test.
Exactly. These Chapter 14 problems show just how much you can do with computational geometry, solving real-world problems with shapes and spatial data.
It's really cool to see how it all comes together. So that's Chapter 14, but there's still more to the book, right?
Yep, there's an appendix all about programming contest strategies. It's like a guide for anyone who wants to compete.
So tips and tricks for the competitive scene.
Exactly. Teamwork, practice routines, managing your time, even dealing with the pressure of competition. It covers all of that.
So it's not just the technical stuff, it's the mental game, too.
Exactly. And it talks about how solutions are judged, how to improve your chances of winning, really gives you a peek behind the curtain.
Sounds like a valuable resource for anyone serious about competition. Well, this has been quite a deep dive. We've covered so much in this book. Programming challenges, data structures, sorting, graphs, dynamic programming, geometry. It's a lot to take in.
It's a lot, but it's also incredibly valuable stuff. These are the tools and techniques that make up the foundation of computer science. And the book does such a good job of explaining it all, making it approachable and engaging.
I agree. It's definitely inspired me to dive deeper into some of these topics, maybe even try out a contest or two.
That's great. Remember, the best way to learn is to do. Experiment, explore, and most importantly, have fun.
Great advice. Well, on that note, thanks for joining me on this deep dive. I hope our listeners are feeling inspired to tackle some programming challenges of their own.